elliptic and parabolic equations and applying them to conservation laws, which are hyperbolic equations. And that's sort of the main thing here. How do we use these techniques in a very different setting than where they originally intended? So the first half of the talk will be basically compressible fluid mechanics. So the intro, motivation, and the results are all going to be stated in terms of compressible fluids. But we're going to be using the kinetic formulation to prove all the results. So the second half of the talk will be very kinetic theory heavy. So the proof sketches. And so without further ado, I'll begin the introduction. So I am going to be talking about one-dimensional conservation laws. And so these are equations of this form, where I have one space derivative and one time derivative. And my unknown is the vector u. So I'm actually looking at systems. And all right, so this is a typical kind of equation for 1D compressible fluid mechanics. And it's known that, okay, weak solutions to this are very bad if you don't impose other constraints. And so what you actually look at are what's called entropy solutions. So an entropy is a function eta such that when I take the gradient and multiply by the gradient of the flux, this has a potential. And entropy solutions for satisfy that. If I have an entropy, I get some extra information about my solution. So I have another sort of inequality. And this sort of is where the time irreversibility comes into play, because this equation is very time reversible, let's say. And so that's sort of like the typical notion of entropy here. I do want to mention, though, if you're not familiar with compressible fluid mechanics, 1D fluid mechanics sounds very strange, and why are you doing this? So the reason is there's sort of two main difficulties for equation of this form. One is going to higher dimensions in the number of variables. So if I looked at a multidimensional thing, I'd have a divergence here. And you have waves everywhere, and the difficulty there is you have more complicated geometry of the wave fronts and so on. So we're avoiding that difficulty. But there's also difficulties when you go to systems, where systems are sort of physically relevant because Euler equations describe the momentum moving around, conservation momentum, which is in higher dimensions very much a system, let's say. And so for systems, the difficulty is, well, you lose maximum principles, for sure. And the other thing you lose is the fact that this is no longer a trivial condition. In one dimension, saying that this gradient has potential is just saying I can integrate a thing. So if I have a scalar thing, I have tons of entropies. But in general, for conservation laws, when I have a system, I might have exactly one entropy. So when I say, okay, I get extra information from this, I might get exactly one additional inequality to work with. So you really care about going both directions, but you pick one to work with, essentially. And one today is working with systems. So the system that we're...
Do I ask a quick question? To go back.
Sure.
So if we think of you said as a vector in Rn.
Yes.
Should I think of you as, like, if I had a one-dimensional fluid, which is in domain one dimension and brain one dimension, you as like a whole load of things that might be conserved about it, and that gives me a
exactly.
vector.
So
okay.
U is going to be the state vector. So actually, the next slide has an example.
Oh,
That's the main example,
brilliant.
Which is the Euler equations. So here, U is changed, but it would be the vector of momentum density and mass density. So the conserved quantities is the state vector. So the first equation is momentum conservation, density conservation, mass conservation, but transport of the mass density, and the second is conservation. And here, for compressible fluids, you have to choose a pressure law. So the pressure law we're choosing for today is that the pressure is a function of the density and it's a power law. So this is the standard things called Isentropic Euler with in particular gamma. And let's say one comment. So this is going to be a talk based on the L infinity theory. So our solutions are going to be L infinity solutions. We're not assuming any regularity, like BV, so bounded variation or locally bounded variation, anything like that. And this is a big difference than if you actually assume some regularity, which we'll see very shortly. And in this setting, existence is well known, global in time, and it's through compensated compactness. We talked about that in 79. This is like pretty classical that you get actually global in time solutions. The question is, are they unique and are they stable and things like that? Because it's isentropic, the temperature goes away and you don't have to.
So the energy conservation.
Yeah, it's because the pressure only depends on density. Decouples. You only need to solve for these two. So in this framework, the standard thing is, okay, you don't actually have smooth solutions, but you have discontinuities develop, and these are called shock waves. So the simplest one is if I have here in space-time, a piecewise constant function. So to the left of this red line, I have a constant state UL, and to the right, I have a constant state UR. So this is kind of what a shock wave looks like in the space-time variables. Now, if I look at, now on the x axis, I have my position, and I have my state space on the y-axis. I actually have what looks like a jump here from the state UL and the state UR. And this is the wavefront, and it's going to move to the right at some given speed. And one important thing is it can't move at any arbitrary speed. It has to move at a speed given by this condition to be the solution to the equation. So this is called the Rankine-Hugano jump condition. And one other thing has to hold. We need the entropy conditions to be satisfied. So we need this condition, which means that essentially information is destroyed. So characteristics crash into the shock, they don't accomplish. And probably won't have to worry so much about that. In this context, I want to mention basically there's a technique from first developed in incompressible fluid mechanics called convex integration, where you can construct additional solutions that are physically meaningful for maybe the study of turbulence or the energy cascade there. And the basic idea is you play with frequencies and you're able to construct very non-unique solutions with the same initial data and for low enough regularity, let's say. Here, in the study of compressible fluid mechanics, basically, people know how to do it in the sense if I take a 1D shock and I stick it in 2D, consider it as a planar shock, then you can do similar things and convex integrate and come up with non-uniqueness. It's not known how to do it in 1D though. And this comes from the entropy conditions or weird 1D things like this. But even in when you put the convex integrated solutions in 2D and you look at them, they have a typical property, which is if I have a shock and I try and do this process of convex integration, what typically happens is I get something that looks like this green function. Hopefully you can see it. Well, basically, it looks pretty close to the, in the smooth areas, it's 12 meters. But as I get to the shock front, I get like order 1 oscillations that are really high frequency. And what you can see is, okay, I need to have UL on the left here and UR on the right. But the sense in which they're obtained is very weak because it's basically, I have really high oscillations and they're averaging out to give me the right state. And this is very characteristic for convex integration solutions. I don't have any sort of strong limits. I have high oscillations right near jumps. And so we're going to say today that's basically going to be the main distinguishing feature of the solutions. So the main, yeah.
Can you just remind me, what is norm for BV? Is it existence and uniqueness?
I'll get to that in like one more slide. But the main question for today is basically, can we, when are these types of solutions physically relevant? And we don't know how to do this process in 1D. So does that mean there's some special structure in 1D that rules this out? And even if there isn't, is there a meaningful criteria that you can develop to say when they are physically relevant or admissible, things like this? And in the back of our minds that we want to go to higher dimensions. So we want something that sort of behaves nicely, but maybe it's just a bit simpler in this case. Right. And so I want to introduce one more kind of idea before talking about BV uniqueness, which is kind of trace properties. So this is, if I have a solution that's defined globally in time and space, I want to be able to say, okay, if I pick a curve, say h of t here, I want to have boundary values. I want to be able to evaluate my globally defined function on this curve. And so the formal way of saying this is, all right, let me translate the curve a whole bunch. So this is adding this y here, translate the curve, and then this generates like a whole area. And over that area, I take some, here it's L1 in time, L infinity in space, over that region, and that should, as the region converges to 0, I should get some meaningful answer. And this is basically the way that I want to say, all right, if this converges to a meaningful answer, that should be the trace. This is the boundary value. Make sense? And so with this in mind, basically it's really hard to prove that a priori these kind of trace properties exist for even scalar equations. So there was a whole bunch of work with this at the beginning of the 2000s. And more recently, sort of kind of wrapping up with the latest work of Celestia. And for systems, which are what I'm talking about today, there's exactly one to line of, which is for gamma equals 3 Euler, and it's for traces in time. So instead of when I had lines that go like vertically, they should go horizontally, and you get traces there. Okay. And the other direction is, okay, what if we just assume the regularity? What can we get? And this regularity would be BV regularity or trace properties. So if, the best result that we have for like 2x2 systems is here. And I should mention, so this is two papers, one of which I was involved in, but this built on a whole bunch of work from several decades. And basically the result is if I have small BV initial data, and I have two functions that have trace property, they're equal. Or two solutions that have the trace property. So you can get uniqueness if you assume on the more regularity. Sorry? So this actually works for any 2x2 system under reasonable hypotheses of flux. So it includes what? It's only for 2x2 systems, though. It's one restriction.
What makes it so hard?
If you go to higher number of systems, you get more and more waves. And so you can only handle like interactions between extremal families of waves, so like 1 shocks and 2 shocks, which it starts getting technical, so I don't want to go in that direction. But when you have a middle family, everything sort of breaks down. At least the way we know how to do things now.
We have better example of scalar case.
Oh yeah, scalar, you have arbitrary uniqueness for just any no smallness, no regularity, nothing. And that's a very special case. And that was known back in the 70s, actually. It's one of the original areas where you use doubling of variables. It's proved due to Khrushchev. And you can actually prove that you have an L1 contraction property for all of the solutions.
When you say scalar, you mean one by system.
So one spatial dimension and also only one type equation. So now I think I've introduced the basics and I want to talk about my results. So the first result is basically if you have, I want to say there's another type of trace property, which is basically the same type of thing as before, but I've changed the norm. So it's the same picture of, I want boundary values, but the norm over those shrinking regions is now changed. So it's L infinity in space, L1 in time, as opposed to the reverse. And so for gamma equals 3 Euler, and bounded solutions, we can say a priori you have that trace property. It's directly from the equation. Any entropy solution should have that. There's no smallness condition. What else? Yeah, but this isn't enough to match the uniqueness. Okay. Right, so I have the supremum outside the integral as opposed to inside. So this is a weaker trace by a little bit. And so just to give you an idea of why this is maybe nice, so it rules out like the worst kind of pictures that you could imagine. So you shouldn't have something like this profile, because here I have a weak limit, but not a strong one in any sort of sense. It's not quite enough to get you to the whole uniqueness theorem, but it's a start. And one thing is it's also a gain of regularity. It's not just I'm propagating, because my initial data could be any arbitrary L infinity profile. And I pick up that I have traces. So to give you a sense. So here, if I run it for it, one thing to notice is that immediately all of those oscillations sharpen, which means, okay, sort of losing regularity in some sense, right? It's becoming discontinuous. But on the other hand, I'm gaining the fact that I should have a trace. So like you see the oscillations here are much smaller already. So as I converge towards that, I do have a boundary value in strong. Notice the shot kind of absorbs all of these perturbations, which will come up again as a very nice thing. That's everything I want to say about theorem 1. Are there any questions before I move on? So my second theorem is a lot more technical looking. So first of all, if you remember there was this f earlier, that was the flux. If I take a derivative and then I look at the eigenvalues, these are going to be lambda 1 and lambda 2. And these are sort of the characteristic speeds in the fluid. And the second result is sort of a regularity result for these characteristic fields of an arbitrary weak solution. So here, if I start with a bounded solution, and now we have to assume that you're not in vacuum, then basically, if I'm close to a fixed state in L1, sufficiently close, then I'm actually close to that fixed state in L infinity. So this is a type of like partial regularity result in a weird sense. Notice there's this plus here, this positive part. So we can only get one-sided estimates here. And so that'll show you why, hopefully, in a little bit. So I want to say just a couple of things. Basically, if you're familiar with partial regularity results, this is sort of like if I have sufficiently small L1 norm, the L1 norm controls the L2. Is basically what this is saying. This is also saying, in another sense, that my characteristic fields are almost semi-continuous functions. So you have a similar result for lambda 2. One of them is upper semi-continuous, and one of them is lower semi-continuous, like almost. And it also implies that if I try and blow up my characteristic field, the blowups will converge in alpha. This is the main thing we wanted from it. It's not clear why that's important yet. But this is basically based off of the Giorgi that was introduced for conservation, for scalar conservation laws by Silvestri in 2018. But there he gets none of this positive part stuff, none of the characteristic fields, it's just directly on the solution. So our result is significantly weaker because we can only do it one-sided and actually on the characteristic field, not on the solution. Hopefully I can tell you why. If anyone has any idea how to do better, of course, I'd be very interested. Basically, if you can do both sides, what you get is an unconditional uniqueness result for small BD initial data. So, like, fully rule out any convex integration of small shocks, for example. Or at least you rule out physical convex integration of small shocks. That was the original goal, but sadly we didn't actually get to that full result.
What do you mean by blow-ups?
So that'll be a technique that comes up later. Or if you know what it means, it's one interesting thing it gives you.
Before we go to another here, so what do you expect? Do you expect that you have unconditional uniqueness? It's just a matter of technique, and maybe in a few years we'll be able to.
I'm not sure.
Do you think there's an actual?
So what it sort of expects is for Euler, you have a whole bunch of entropies actually. Like you have maybe one that physics tells you is like the best entropy, but then you also have a whole range of more of them. So if you satisfy all of the entropy conditions, sort of suspect that you have uniqueness. So this would be like physical, like, okay, an entropy solution is unique. But on the other hand, if you satisfy maybe just one entropy condition, maybe you can still do convex integration, which would be very borderline. Is that maybe help with it? Yeah, so there's always, okay, maybe you can do convex integration, but then it would be, okay, maybe they just aren't physical at that point, which would be kind of nice to have one situation where you can say, okay, you can do it, but there's something missing and you need some other condition to tell you whether they're actually meaningful. So the last main theorem, which I actually won't go through a proof of today or anything, it's basically related to the idea of generalized characteristics. So using the previous theorem, we gain enough regularity on the characteristic fields to say that, well, we want to try and construct a solution to an ODE that would be h dot equals lambda 1 or something, because this would let you do method of characteristics, for example. So there's a generalized notion of h dot equals lambda 1, should be a generalized characteristic, which is this type of solution here. These were introduced by De Framis and De Perna in 71. So way back when. And we couldn't quite do that because of the one-sidedness. So we got 1/2 of the inequality. And from above, all we can say is, okay, you're less than the scoop of possible values. So you lose control from above. So you can kind of track where a particle goes for an arbitrary solution, but you might overshoot. And so the reason this is important is because of stability theory. If you want to do L2 stability theory for like a shock. So here, this is all run from Berger's equation, but it gives the green feature. So here I have a fixed shock, which should move to the right at a very slow speed. And I've added on some funky perturbation on the bottom one. So when I start playing this, what happens is shock will actually move backwards in perturbation because I've changed the value at exactly the point here. So where it was here, like it was the sine wave looking thing. And the speed of the shock depends on the value exactly at those 2 points. So it starts moving backwards, but then this other shock catches up to it and it starts moving forwards again. So essentially, if I have stuff over here, what's going to happen is it's going to cause the wavefront to wiggle back and forth. So this is bad if I want to compare the two. And the way you get around this is by translating the shock to match where this one is, sort of. And that's the use of the generalized characteristic. That's exactly where you're going to use it. You're going to use it to shift the perturbation and make it match up. And so that's basically why you need that for stability theory. So, any questions there? All right, so those are the main results. So I'm going to move on, and now it's going to take a dive into kinetic theory. And so the first part will be introducing a few tools. And then I'll start sketching things, try and sketch proof of the first two theorems. So there is a nice result due to Leon Critin and Cadmore, which says that for isentropic Euler, you can sort of reconstruct the kinetic function in some sense. So given a solution, bounded solution to Euler, you can write down this function f, which will satisfy sort of a kinetic looking equation. And this is for any gamma. But one thing to notice is if gamma equals 3, theta equals 1, and this term goes away. And if theta is 1, this is velocity times dx of f. This is why we can do gamma equals 3, because it looks kinetic, actually. Sort of. Yeah, so the chi's also become much nicer. Basically, you have this this equation, but you also have sort of rigidity that for every profile, for every t and x, you have to be this chi function, which is a very specific type of function. So through, sorry? It looks sort of like this. It'll be on the next slide. It's a limit of this. And yes, mu has to be a positive measure and finite. And what else did I want to say? Oh, and as normal, you can cover the physical quantities via moments from kinetic function. So rho is mass, which is recovered just by integrating, and momentum is recovered by the first one. And this u, which appears here, which makes the equation really bad for gamma 3, is the momentum over this is the velocity, which is a non-local coefficient. So if anyone has any ideas how to handle equations like these, for example, be very interesting. Because for gamma equals 3, well, here you have a much simpler form. This might look a lot more friendly if you're used to kinetic things, right? I've got transport equals velocity derivatives of something. And here I have the pi function is just becomes a characteristic function of an interval in velocity. And because you recover the moments, or you recover the physical quantities via moments, you can actually say which which interval it has to be. And the interval is between the two characteristic speeds. So this is a much simpler thing, and we actually know how to work with this because it's kinetic looking, say. So the main tool you get here from kinetic theory, maybe I should say, let me draw a picture real quick of what these look like. So I have two curves in red here, my lambda 1 and my lambda 2 that depend on time and space. And in the velocity direction, I say, okay, f is just equal to 1 between the two. in this blue region, and f is equal to 0 outside. And a priori, all I know about these curves is that they're bounded. So I could have a jump, whatever. I do know that they're ordered because they're smallest eigenvalue, largest eigenvalue. But I don't know much more than that. One thing that you might notice here is I can have that they meet even. This corresponds to when I have a vacuum state. So when the mass is 0 at that point. And what's troubling for us is if you have vacuum states, you lose control over where in velocity this is. Right? Two curves can meet at any point. And so this would be a problem that you don't have in a scale case. So, oh, and yeah, if you cut along the velocity direction, you just have a characteristic function. That's from London. So these are really sort of simple functions in the case. And with the kinetic formulation, one great thing you have are averaging limits. This is like nice gains you get. And so averaging limits basically say if I have transport type thing equal to some right-hand side, I gain regularity on the average. So if the right-hand side has a full derivative in time or space, notice I have one derivative in time and space over here. So what I do is I basically gain compactness. I don't actually gain regularity on the average. So the right-hand side, these GKs can be measures. That's why I put total variation mark here. So if I have bounded total variation, one thing I gain is that the averages are compact in LP. This is great because the averages are rho and mass and momentum. And on the other hand, if I only have derivatives in velocity, well, from boundedness, I actually gain some level on the average. And so this will be great because there's a lot of recent work studying how to actually use these properties to gain regularity in the kinetic community, let's say, for like Landau equation, Boltzmann equations, and things like this. So we're following the same approach, but in this sort of different setting. So that's actually basically the only tools I need. So I'm going to try and sketch a quick sketch of theorem 1. So the first thing you do is you try and prove that, okay, I have some trace, I have a weak trace. So this is when, if you remember the picture where I have those regions and that are shrinking, then I should have convergence and weak topology. So here, the way you get that is by saying, basically, all right, let me multiply by a test function that's only in time and velocity, not in space, and say that, okay, the space, so as I shift, and that's actually a BV function. So if I've integrated out in time and velocity, I get a BV function. And what's great about BV functions is they have limits, right? This is one of the great properties. They have right and left limits. Okay, maybe not the same, but we would expect them to be the same place. And we have another a priori estimate, which is all of these functions are bounded by 1. And the characteristic functions of it. So we have a uniform L infinity bound. And so combined, weak star compactness and L infinity plus this property is enough to get you some sort of matrix. And from here, we want to upgrade this convergence to a strong convergence. And so what I have here are characteristic functions, which are converging to some fixed function weakly. Basically, it's enough to show that the limit function is also a characteristic function. and then characteristic functions that converge weakly to a characteristic function converge strongly. So this is now where we start using blowups. So the idea behind a blowup is, all right, let me fix some point along my curve. And now I want to look at a fixed window of scale epsilon. So this is a small scale window. And I want to blow it up to a size 1 window. And the way I do it should preserve sort of the structure of the equation, which I'll show on the next slide. But it should also here I'm taking things along the curve. So what happens is the curve straightens out to be like the y=0 line here. And everything to the right of the curve stays to the right half plane. Everything to the left of the curve goes to the left half. And the idea is that, okay, I still solve basically the same equation. And what's great is this part by Lebesgue points theorem will converge to 0, the coefficient there, because H is Lipschitz, and H dot is well defined almost everywhere. And so this whole term converges to 0 and like H minus 1 or something. Basically, I have one derivative here and for this term, basic measure theory, after you stare at it, and will tell you that you can pick a sequence of scales so that the total variation of the measures will go to 0. They go to 0 away from the axis. So they go to 0 here on this side and here on this side. And this is because there might be a shock present along the axis. And if there's a shock, measure. And so what happens is averaging lemmas tell us there's a limit, first of all. And these are what I'm calling this plus or minus infinity. And because the right-hand side vanishes, we get this simpler equation. And notice all of the derivatives are in tau and y, which are these local variables of the blow-up window, not the original variables. So this is actually a constant coefficient. It's just a transport equation. So what we've got pictorially is over here, there's some limit which solves a transport equation. Over here, we have a limit which solves a transport equation. And using the structure of the equation again, we're able to say that basically the boundary value, which is along here, is actually the weak trace on both sides. So once you have, but it's the weak trace in the global variables, not the local ones. So it's actually constant in global variables. So if you have a transport equation with constant initial data, your solution better be constant. And so this is a rigidity result that lets us say, all right, my blow-up limit is at plus minus infinity is actually a constant function that's the weak trace at right point. And weak trace then will have to be a high function having to get strong. Basically, this is a compact rigidity in some sense. And we're using rigidity of the transport equation at the end. Any questions? Well, next I will try and use any time to sketch a little bit about theorem 2, which I think is the more interesting or more novel in some sense. So in a picture, just let me rephrase theorem 2. Theorem 2 basically said, if I look at a solution, which now I'm converting to the kinetic framework, So I have these two curves. And I'm doing it for lambda 2. And if I look at this yellow region, which is basically where the function is above a fixed state. So, and on like a larger space-time region, so B2, then if the yellow area is small enough, then if I shrink the region, so to this blue B1 and to a smaller threshold, right, small, larger threshold, so a smaller area, then this should actually be 0 in infinity. So 0. So basically the theorem is if this yellow region is sufficiently small in area, then the purple region should be non-existent, it should be 0. And this is a version of like a Giorgi, or will be proved via version of Giorgi. So where I'm going from a larger region to a smaller one. And so in the larger one, if I'm sufficiently small, then the smaller one actually 0. This setting. So the first step in an argument like this is, okay, I need an energy inequality. And so if I go from a larger region to a smaller region, what do I gain? And so here, you can use averaging this. But now, for a reason, I'm including more terms over here. And if I only have the v derivatives, I actually gain Sobolev regularity. And now I can use Sobolev embedding and Holder to come up with an energy inequality that looks like this. And this L2 became an L1 because everything's 0 valued. So if you're familiar with the Giorgi, what you want to appear is a control quantity and the control quantity to a power and something that looks like a level set thing to another power where the sum should be bigger than 1. Here it's less than 1 right now. So that means we have to gain something from these measures. So that we, in total, have the power greater than 1. So the setup is now going to be, all right, I'm going to have a whole bunch of space-time balls that are start at radius 2 and shrink to radius 1. And I'm going to have level set heights, sort of quote unquote, classical to Giorgi, that go from some height, some threshold to threshold plus epsilon. And my control quantity is going to be weird for anyone who's done Giorgi. It's not, I'm not looking at sort of scalar thing and subtracting off the level set rate, taking the positive part. What I'm instead doing is looking at the L1 norm over a particular region in this space-time velocity space. And this will be sort of the control quantity. And because it's a system, we don't actually, this is sort of where things diverge from the scalar case. You can't subtract off something from a system and say, take the positive part. Types don't work. So, and in this study, basically, all right, we try and localize the energy inequality. And here, because we're shrinking in velocity space, you have to localize in velocity. And you don't have to do this in a scalar case, which makes everything work there much nicer. So when you localize, this is where these measures come up. You gain derivatives on the test function for these measures. And now what you have to do is bound the total variation of these measures. And you want to use this set to get back to control quantity at the previous step. So let me say this argument is exactly where everything breaks. The localization velocity. If you're familiar with kinetic theory, localizing velocities is really hard. And so here, we need that total variation on a range of velocities is bounded by, there's a typo, this should be the same set in velocities of the kinetic function. And this is our control quantity. So basically, there's this mysterious L here, which I failed to mention what it is. But this is like something that's sufficiently large that's beyond all of the graph of all of the pictures I've drawn. So I can do it from for velocity ranges that go beyond where any of the velocities for f are. But I can't do it in the middle region. If you do it on the endpoint region, the argument's really easy. You test the equation with something that looks quadratic in velocity, integrate by parts twice in velocity because I have two derivatives, and this gives me what I need. It gives me the right estimate. We cannot figure out how to do this. So this is if I have an intermediate range of velocities. Let me show you on the picture. So if I have a velocity range that's like here to here, so like from B to B plus epsilon, something in the middle. We don't know how to balance the total variation measured by the kinetic function locally there. And because we don't know how to do that, we can't do where all the one-sidedness comes from. So, but when you're in the regime where we can do something, do it. And the other thing is corresponds to using the Chebyshev for normal to Giorgi. What we actually need is a mass gap. We need to assume that we don't have any of these vacuum regions where the two curves touch to be able to actually use the level set size to get back to the control point. And the upshot is, if you assume what you need to, you get an inequality of the form. Your control quantity at the next step is bounded by the control quantity at the current step to some power bigger than 1, which means that if the initial data is sufficiently small, so if U0 is sufficiently small, then the one in the limit is actually 0. And the one at the initial one is exactly going to be this is the yellow region area, and this is going to be the that area in the purple region is 0, which means it's not there, so it's 0 now. And so this is a rough sketch of other arguments. So I'll stop here. Thank you.
Are there any questions? Relation on the right hand side, the measure function.
One second. So, like this mu.
So where do you
So this measure is called the entropy dissipation measure. It's effectively comes from. Actually, tell you this. Right. So here, when I have an entropy and I take derivatives, I gain a sign. This is enough to say that basically this left-hand side is a measure. Because it has a sign in its distributions. So it's enough to say it's a measure. And it's actually basically the measure that appears there. Which actually gets to an interesting point. The reason the kinetic formulations work is because I have enough entropies.
So Giorgi, that's it. Just
Except, but
plus because the equivalent of the plus equal to Giorgi, but you just
yeah, so I only did the L2's L infinity. Problem with doing anything more is you can't get C alpha, right? I have
yes,
shocks.
yeah.
There might be hope of if I'm away from a shock enough, then I can get C alpha saying I'm swinging away from shocks. But I don't know. You definitely have to be careful. Shocks.
So at the very end, so you think that at some point there is an issue with localizing things?
Yeah,
Um,
right here.
yes. So the very last line. So are you able to do something where instead of the integral from A to B on the right hand side, you do something maybe larger or something like that? No?
So the problem is, it seems like well, this can be 0, and this doesn't have to be. For example,
Yeah. So but you know that if the integral of f over the whole line is 0,
yeah,
then mu is 0. If f is
Yeah.
identically 0, then so mu.
right, yeah,
So you may not have that inequality, but you might have something maybe a bit different where you enlarge the space of separation in the right side.
So we've tried, we weren't able to get anything. It's not saying that we can't, but we also couldn't prove that we don't get anything. But the basic problem, let's see if I can find this where is the fact that there's 2 derivatives in V. And it's not obvious why that's a problem, at least to me. In the scalar case, you get 1 derivative in V, and everything works golden late. But with the 2 derivatives, it seems like what happens is you have some non-local effects in velocity. So like you can have f be 0 over a range, and mu has derivative 2 derivatives 0, but that doesn't mean it's not actually present still. And it looks like it can actually be present even if f isn't. So that's sort of really the problem. We weren't actually able to construct anything where blatantly failed, but we kind of gave up on trying to get inequality.
Right. Well, let's thank Will again. And we'll be back here in 55 minutes for the next talk today.